we have Alex and McCaulay talking about charging ahead, exploiting an EV charger controller at Pwn2Own 2024. So over to you guys.
Thank you. Hi. Hello and welcome to our talk on exploiting an EV charger at Pwn2Own 2024. I just want to do a quick introduction into who we are. And if you're not familiar with us, I'm Alex Plaskett, and this is my colleague McCaulay Hudson. We're from NCC's Exploit Development Group. And also, what is Pwn2Own? I think a lot of you are probably already familiar what the competition actually is, but I'll just give a quick overview. It's essentially a yearly vulnerability research competition run by Trend Micro, the zero-day initiative. And essentially, there's multiple different iterations per year. You've got the Pwn2Own desktop, which is focusing on desktop software, so things like web browsers, enterprise-level software. Then you've got Pwn2Own Mobile, which originally was focused around mobile devices, so Android, iOS, mobile things, but they extended that recently to focus on embedded devices, so printers, NASs, routers, and so on. They've now pulled into scope. And then there's Pwn2Own Automotive, which is the latest which ZDI have introduced. And this is just focusing on automotive security. It's just, anything related to automotive stuff. And this was the first iteration as well this year, of the competition. So the competition, it's essentially to compromise a set of targets. You have to gain arbitrary code execution, remote code execution against those targets, and fully compromise the target. The prizes as well are based on the level of perceived difficulty which ZDI kind of think the target should be based on their vulnerability information they've got and the research which they've done themselves on the actual targets. Then finally, ZDI purchased these vulnerabilities or exploits from the competition if you're successful, and they provide them directly to the vendors. So there's no sketchy exploit sales happening here. They're actually just the disclosure meetings are with the vendors as well, and they're helping the vendors to improve their security. This is just a minor note, but the venue for automotive, it was in Tokyo, big site. It was a pretty cool venue in Tokyo, absolutely huge, and there's a big kind of convention going on at the same time as the competition. So the automotive targets then, they basically, there's the things like Tesla. There's a few different categories for Tesla. Then you've got the in-vehicle infotainment system, which we're not talking about today, but we actually entered that category and we looked at the in-vehicle entertainment systems. These are aftermarket in-vehicle infotainment systems. Then you have the electrical vehicle charger category, which is what we are talking about today. And then finally, operating systems which are used within the automotive space. So things like automotive-grade Linux, BlackBerry QNX, and Android Automotive. So the rules of the competition, if you're not familiar, then as I said before, it requires unauthenticated code execution on the devices. If there is authentication there, then you have to bypass it. You can't use a vulnerability which already gives you you start in a privileged position. You have to start from zero. You're allowed 3 attempts at the competition, and each attempt has to be done within 10 minutes as well. Has to complete. If your exploits aren't successful within that time, then you've failed, basically. Now, the automotive was quite interesting because in previous editions of Pwn2Own, they didn't allow physical access, they didn't allow physical presence. But in automotive, because the types of devices, such as EV chargers, are available in public spaces, are in a standard usage pattern, or an attacker could actually have physical access to these, so it's not just remote attacks. And also, things like hardware attacks, like you're not allowed to perform hardware attacks as part of the competition. Like you can't just start opening up devices, like soldering onto like debug connectors and so on. You're allowed to do that in like preparation to kind of like to gain like visibility of the platform and gain capabilities on the platform. But in the competition, it has to be done like as a sort of standard usage pattern of a user or exploit over the network. So why is EV charger security important then? Well, in the UK, the UK government's trying to ban the sale of petrol cars in 2035, I believe. That's what their targets are at the moment. And we can see that like EV infrastructure is increasing. There's a lot more like EV charger like being installed across the country. This graph basically just shows like year on year the EV infrastructure is growing across the UK, and in 2030 there's expected to be at least 300,000 EV charging. These are just public EV charging points. These are not charging points which are in people's homes, the residential chargers. These are just ones which are in, say, public locations. And the UK is kind of has like a smaller share of the market, smaller share compared to somewhere like China, where there's a lot more infrastructure being deployed. There's a lot more people. So the EV charging category, it was created by ZDI, I believe, to kind of give a good cross-section of the market, to give like different, like some residential chargers and ones which could also be deployed in more like public locations. So we kind of categorize these different chargers into private residential, so ones which are installed in people's homes. Then public charging point operator ones, so they would be the ones which you'd see in like maybe a supermarket car park or a public location. And then finally, like the strategic road network. So this is things like the motorway network across the UK and like motorway service stations and things like that. So the device which we were looking at, which we're talking about today, is actually, it's not a residential charger. It's one which is used for building your own EV charging infrastructure. It's the Phoenix Contact Charex X3100. And this is basically a component within building your own EV charging infrastructure. You basically take this and combine it with things like the actual like connector leads which go into the car, and the power distribution units as well, which actually provide the power. The Charex, the control module, is essentially the management for all of this, and it's like a Linux embedded system which is running inside, like on the control module. It has things like it uses the Open Charging Point Protocol, OCPP, and you can configure it with back-end OCPP servers and manage your charges and so on like that. It also has connections. You can also set it up to do vehicle-to-grid communication as well. And one thing to note is as well, this device, it's quite like developer-friendly. It's got REST API documents. It's got MQTT API documentation, because it's kind of like a solution which you integrate into your own like EV infrastructure. So from an attack surface research perspective then, like how did we go about examining this device? Well, the first thing we were doing was essentially understanding the physical interfaces. Like if somebody had physical access to the device, what could they do? Like which interfaces could they plug into? And what is the implications of these interfaces being exposed? Then we have the device state, which is something which is quite specific to Phoenix Contact, the Charex, which you can have a client mode and a server mode, which I'll expand on in a second. And then finally, the external services as well. So these are like the network accessible external services like open ports and outbound communication interfaces. So this is what the CharX looks like from a physical interface perspective. You have you have a SIM card slot, which allows vehicle-to-grid communication if you've got it configured in that mode. You've got the micro SD card slot. You've got a USB port, which is used for potentially admin interface to the control module if you don't want to configure it via Ethernet. And then you've got 2 Ethernet ports, which would connect it to the network. You'd have a LAN Ethernet port and a WAN Ethernet port. So this concept of device state as well is interesting because you have a server and a client state, and the CharX can operate in each of these different modes. And based on the mode which is currently operating in, then it would expose different services. So you could have one CharX, which is in server mode, and then you could chain off in a daisy chain configuration. You could have clients which are managed by the server CharX. And yeah, and that would change the attack surface and based on whatever mode it's in and what services are running on there. And then the other thing to mention is the different outbound communication. So based on whatever mode it's in, is like the traffic which is initiated from the CharX outbound. So from an attacker perspective, what does this mean? Like, can we trigger mode switches, and like, does this give us anything interesting? Well, actually, we can trigger a server to client mode switch by just being running a DHCP server on the 192.168.4 range, advertising that DHCP lease on that range, and the device will basically take that and do a mode switch from server to client. And then there's also the ability to turn the device from a client to a server by, this is actually a vulnerability, I think, in itself, so normally you would only be able to configure to do the mode switches like this by the web interface. An admin would be able to log into the web interface with operator permissions, but we found a way to interact with the service and basically swap a configuration setting which changes the system name to EV3000, and then that'll basically turn it from client to server. So the external attack surface then, if we're starting to examine it, like what is there actually there to attack? You've got your standard services, so you have things like SSH running on there. You've got the custom services like the CharX website, the admin interface, and then you've got standard things like Mosquito running on there, NTP, MDNS. But the interesting thing to draw is, as I was saying, like the attack surface varies based on whether you're accessing it from the WAN port, whether you're accessing it from the LAN port, and whether it's in client mode or whether it's in server mode. So we just kind of mapped out what was available where. The custom services, they're obviously an interesting thing for an attacker to look at. It might be easier to find vulnerabilities in custom services because they would be written by Phoenix Contact. And so the web interface, it's just on port 80. The admin interface is on port 80. You've also got the REST API on port 5000, and then a number of other custom REST services which were undocumented, and we had to reverse engineer to actually understand the APIs for those. And then finally, I just want to talk about, quickly about a tool which we developed in-house called Firmalizer. It's for automating the analysis of IoT devices or firmware images. So we'd provide it with an unpacked firmware image, and it would basically just pull out interesting things which we always kind of asking about these devices for Pwn2Own. So things like what are the users on the device? Are there any, like the password files? Like what binaries are running on there? What mitigations are applied? Are there mitigations? But essentially, this tool is more it's to aid a manual analysis for vulnerability research afterwards. It's not like a VA scan. It's not like a scanner which will find vulns straight away. It's something where it'll help us focus down on the critical areas which we want to investigate more by default. And it also allows diffing as well, so we can diff firmware images against like previous firmware images, and we can notice when binaries have changed and the mitigations have changed and so on, which might be worth investigating. I'll hand over now to McCaulay to talk about the reverse engineering.
Thank you. OK, so onto the reverse engineering of the actual device. We have the static analysis and the static reverse engineering we did, which was on all the custom services. And then we also went and did a bit of dynamic analysis by using some emulation in Pwn2Own. So starting off with the static reverse engineering, a lot of the binaries that Phoenix wrote were wrote in Python, which was promising, except from they used a tool called Siphon, which converts Python code to C code, or C++ code. And that made it a lot more difficult to reverse engineer because, for example, in the right-hand side, if you can see that, there's a simple print hello world in Python. That one line of Python generates about 4,200 lines of C code. So that's 4,000 lines of boilerplate code, and then about every one line of C code every one line of Python code results in about 50 lines of C code. So all of a sudden, this tiny little bit of Python code ends up in a huge amounts of C code, which you need to reverse engineer. So once this is in Ghidra, it looks something like this, which is quite difficult to reverse engineer. But by looking at how Siphon is implemented on GitHub, we can sort of slowly puzzle the pieces back on how to reverse engineer it to Python. So we created some scripts to retype the symbols, rename the function variable and variables. There's also a structure, which is called string tab, and it's essentially the strings table. So all the strings from the Python script get put into this strings table. And then if you can reverse engineer that strings table and look at the references to the strings, you can see where those various Python strings have been used in the C code. We could add them as comments into the C code, and then we could sort of puzzle, rearrange the puzzle pieces back and reconstruct the Python from this C code. So by doing that, we're not going to get an exact copy of the Python code that they wrote, but we're able to reverse engineer it enough to be able to read the Python code and maybe potentially find some vulnerabilities. So this is, for example, an install application function, which was compiled to C, and you can kind of reverse engineer the variables and what functions were called and the strings that were passed, and you can sort of build a picture of what the code's doing. So that was mainly the static analysis side. It was quite time-consuming, even with the scripts. And the issue was we didn't have much time for the competition to start, and I think it was multiple weeks for the actual device to be delivered to us. So we was doing all this static analysis, but we potentially finding bugs, but we couldn't actually interact or do any debugging. So while we was waiting for the device to be delivered to us, we started to emulate the firmware using Pwn2Own. So you could download the firmware from the vendor's website. It was not encrypted or anything, so you could just extract the file system, and then you see it through with Pwn2Own to emulate the device. We had to do various bits of configuration file changes because the custom services expected config files in particular places. We modified them to enable all the debugging information so we could get as much information as possible. And then we're able to run all these various different services on our emulated environment locally so that we can begin testing and playing around with some of these services to see how they work and if there's any vulnerabilities there. So from this, although some of the services required some hardware features, so not all of the functionality worked, the vast majority of it did. So before it was even delivered, we had a semi-working environment where we could actually test some of the potential bugs we found. So now on to the first vulnerability chain we found. So this we didn't use for the competition, reported it afterwards. And essentially, the default account on the device, you have to change the password when you first set it up. However, when a firmware update happens on the device, for some reason it resets the user password to default credentials. So if we could figure out a way of how we could force a firmware update on this device, Bear in mind, in the competition, it has to be on the latest firmware. But if we could somehow do that without any authentication, without logging into the web app, etc., then we could maybe reset it to default credentials. So the very first thing we needed to do is trigger it to from that server mode to client mode. And to do that, we just run a DHCP server on our host on this 192.168.4 range, and that will trigger the Charex to think it's a client to us and think we're a Charex server. And once it's in client mode, it starts to talk to us as if we are the server. So it performs HTTP requests, asking if there's any firmware updates available. So we just run a fake web server, and we just say, yes, there is. There's 9.9.9. And that will make it think, OK, there's a new update. And when it asks us for the latest firmware, we just pass it the latest legitimate firmware from Phoenix. So, and the reason this is because it's signed, so they do verify the firmware's not been tampered with, etc. But interestingly enough, as long as it's on the same version, firmware version or higher, it will still install it. So it'll install the firmware even if it's the same version. So we can just pass it the latest firmware and it'll always install it. And then it triggers a reboot. And then once that reboot occurs, the user credentials will then be being reset. So here, that is a screenshot of that. So once it's rebooted and updated that firmware, you can just SSH in, use the password of user. It says it's expired, and then you can control what the new password is, and then you have low-level user access to the Charex. So here's a demo of that. So initially, we're running that DHCP server to trigger it to change states to client mode. Once it asks for the DHCP request, it'll change to client mode. Second. And then once it's in client mode, it will, the HTTP server is running on our host, and then the client performs the GET request, downloads that firmware, and installs it. And then after that's installed, it should reboot. And then once it's rebooted, we can attempt to log in via SSH. And then we can log in as SSH through SSH and log in as the user app user. For Pwn2Own, this was enough, just having that low privileged user. But as I said, we didn't use this vulnerability, we used a different one. So we wasn't 100% sure if this would count or not, because it was a bit of an unusual vulnerability. So this was the CVE for that, CVFS 8.6, and essentially from a firmware update resets the user account to the default password. So this was another vulnerability we found just during the looking at the device. Again, this wasn't used in Pwn2Own because it wasn't required, but as part of the research, we needed root to get more access so we could debug various vulnerabilities we found. And this vulnerability was quite a simple pre-risk because they had custom scripts in etc sudoers, and one of those scripts which is able to run as root past user input to tar, and then you could use that to pre-risk. So as the user app, either because you control own the device or because you use the first vulnerability, you can log in through SSH as the user app user. And then if you check the sudoers file, you can see there's various Charex commands, scripts that can be executed that have been wrote by Phoenix Contact. And one of them is the Charex pack logs. And this script, if you can read that a bit, essentially takes an input parameter, which is just a file name, like for example, example.tar.gz. And it will eventually just run sudo tar and then your input, and then a file log. However, if you notice, the target file at the top is what we can control as the user. And this will run as sudo, so as run as root from using sudo. And because of the way they've done this, you can append any options from tar. So from this point, we look at the man file of tar and see if there's any interesting options we can eventually result in code execution. And there's two that are quite interesting. There's this -- checkpoint and then checkpoint action. And essentially what happens is when a checkpoint occurs, it will trigger the checkpoint action. And the checkpoint action you can do as exec, which will execute a command. So this is a way you can abuse this to get root code execution. So you pass it the file name, and then you append the checkpoint parameter, and then you do a checkpoint action of exec as just bin sh. So then you get the root shell. This was reported to ZDI afterwards, and it was already a duplicate report. But there's a CV for that one. Essentially, input validation. Now onto the final vulnerability we identified. So this is the one we actually used end-to-end for the competition. And it allows you to execute a shell script by doing a config injection. And essentially the way we do that is we start in server mode, and there is a charx endpoint, which was a custom endpoint, which allows you to upload an arbitrary file, which is our script file. And then in client mode, we can configure a cellular network, perform some config injection, reboot, and that config injection will execute that script as root. So going into that a bit deeper, we begin with the uploading of an arbitrary file contents. So this was a reversed function, return database. And essentially, they had some validation on the file name. So you couldn't do, for example, path traversal vulnerability. But there was no validation on the actual file content, so it didn't have to be an SQLite database, which is what they was expecting. It could be actually anything. And for some reason, the file was uploaded with executable permissions. But I don't know why, because it's a database file. And the file that gets uploaded is stored in this fixed path on the charx, which is duplicate_abcd.db. So using this endpoint, we could upload a script file that we can fully control because there's no validation. And this will plant the scripts that we are wanting to execute on the file system. At this point in time, it's not going to be executed by anything, but it's there as kind of like a setup. And the actual script, we first did a light show. It just was a way in the competition to prove that we've got root code execution. And then we also reset the password for the user and reset the root password. So now that file's planted on the file system, we need to change the device into client mode. And again, we just do that by running a DHCP server. Once it's in client mode, there's this system config manager service. And this one allows you to set config values on Authenticated in this configuration file. This configuration file is specific to Phoenix. However, some of the values within that configuration file then propagate into the PPPD, which is the point-to-point protocol configuration file, which was quite interesting. That was inside the cellular network section. So the very first thing we tried was trying to inject like new lines to try do a config injection in that PPPD file. However, there was some validation on the inputs we was passing, so that didn't work. But what was interesting was when we was reading about PPPP, it actually parses multiple options on the same line if they're separated by a space. So at this point, we were thinking we could just add a space and then add any configurations we wanted. So the next step was thinking, again, what other configurations can we use in order to benefit us in some way? So reading the PPPD config options, you have the three interesting ones, which is init, connect, and welcome. And they trigger on certain events, for example, when you're attempting to connect to a cellular network. And the script is just a file path to a script that you want to execute when that triggers. And luckily, from the initial vulnerability, we have a file that we can control that's executable with any contents we can control. So by setting these configuration values to that original script, when these events occur, it will execute the script. So again, this was just a REST service endpoint to set those configuration values. So most of them are just set up normally, and then, for example, this idle disconnect is set to 3,600, which is the normal value. And then we just append the other options that we want to set with a space. So we have, like, so for example, the welcome option, and then the file path to our script, and then connect, and so on. This didn't have to be in the idle disconnect option. It could have been in some of the others which end up getting propagated into PPP. It didn't really matter. And then we need to then swap it back into server mode in order for it to attempt that cellular connection. So for this, we just set the system name to EV3000 through that exact same service. And this causes it to boot into server mode. And then there's another endpoint which just lets us reboot the device, unauthenticated. And this one just was used to trigger the actual vulnerability. And then, as you can see, the Twitter thing, that was successful in the actual competition. So we've got another demo of that. Hopefully you can read the code. So on the right-hand side, you've got the device. With the top LEDs should start blinking once it executes. And on the left, we have the code. So initially, we were uploading that script file. It went past quite quickly. And then we're switching the device to state to the server mode. And then we're waiting for the cellular setting service to be up. And then we're setting all the cellular network configuration values, including that config injection, to point to that file we uploaded. We set the system name to reboot it into server mode, and then it reboots. And then if you see on the top right-hand side, we're doing the light show just to prove that we've got code execution. We also got a root shell, but because of the 10-minute time limit in the competition, the root shell was accessible at like 11 minutes or 10 minutes, 10 seconds or something, whereas the light show triggered about 8 or 9 minutes in. So it was more on the safe side just to prove root code execution from the light show rather than from a root shell. So this is the CV for that one. This was the ability to upload an arbitrary script file due to improper input validation. And then that was combined with the configuration injection, which led to remote code execution. Now back over to Alex on post-exploitation.
Yeah, thanks, McCaulay. So I'm now going to talk about what happens when you can actually what happens when you actually compromise like an EV charger, and what have we seen in the wild so far. There's not actually that much prior threat research into this and in the wild attacks. We've seen things like defacement. There's been charging points, like council's charging points hacked to like display rude messages. There's been some hacking potentially to do with the war in Ukraine. But actually it's mainly been kind of like reputational damage for the companies who are involved, and it hasn't really been like large-scale disruption. There's also been like privacy risks around, like they're just traditional like cloud vulnerabilities where data in the access controls in the cloud haven't been configured correctly, and EV charging infrastructure has been using these back-end systems and disclosing leaking data which could be accessed. So if I had to do like a key kind of like overall taxonomy of the different threats, the key threats which the EV chargers infrastructure kind of faces. You've got the reputational damage, the defacement, which is what we've seen so far. Privacy data leakages, as I mentioned, with the like cloud infrastructure. But to me, the scary ones are more like the disruption, and like if you could build a botnet of EV chargers, if you could say ransomware EV charging infrastructure. That would cause like massive problems, like trying to respond to ransomware. or denial of service attacks against, like, say, a whole country. Like, if you could take out their entire EV charging infrastructure, that'd be a massive problem, probably, especially if, like, in the future when all cars are electric. And then electrical grid disruption. Well, there was a paper by one of the American national laboratories. They actually did some research saying that it might be possible to actually, like, to cause grid disruption, like by compromising multiple charges. We haven't really seen this, like, demonstrated in practice, but it's kind of a good future. Like, it's a possible threat. Then you've got things like fraud. You've got power theft. Like, if you can get charging, if you can get charged for free, if you can get a charge up for free. You've got the payment fraud as well. If you can maybe get like compromise the payments back end, or get charging for less than it should be. And also one other threat which I just saw recently, but I didn't add to the slides, is if you could attack the car as well from a compromised EV charger. I saw that demonstrated recently, that people were business communication protocols, like from the car to the charger as well. So in conclusion then, what did we see from Pwn2Own? Well, ZDI, they had about 16 vulnerabilities reported to them in Pwn2Own. I think somebody else is also in the audience who also reported an issue to them. But we've seen different vulnerability classes kind of across the scope. We've got input validation, as you would expect. It's one of the main common weaknesses. Memory safety is an interesting one, because even though Phoenix Contact had gone to quite an extent to write things in Python and Python, they still had quite a bit of native code running on the device, and native attacks, native code vulnerabilities. And then like traditional kind of clear text communication, network configuration issues, firewall issues, that kind of thing, still are. So even with, it's just worth saying, even with, if you're rewriting things in managed code languages, you still have all the logic vulnerability classes to care about. So you may reduce the memory, well, you may remove the memory safety issues, but yeah, you still have to care about logic bugs. Overall, then, I think all of the charges at Pwn2Own were actually hacked, like every single one in the categories. And as a whole, they were mainly simple bugs. Like these weren't really groundbreaking bugs we were talking about in this presentation. They were fairly simple bugs. And there was one of two. There was some other teams who actually did very in-depth exploitation, but it wasn't really needed, because the low-hanging fruit and easier bugs were there. So, which is kind of a sad story, really, from EV charging infrastructure components. There wasn't too much time investment either. So some of the Pwn2Owns which I've done in the past required significant months and months and months of effort. This wasn't a big time investment from my team. It was, yeah. There's also a lot of attack surface on these devices. You've got lots of different interfaces, both physically and network connectivity-wise as well. There's a lot of connections, a lot of back-end infrastructure, and so on. So, yeah, the research access can be pretty challenging. Like the device which we talked about today, the CharX, we could test the control module in isolation. It was just an embedded Linux device. But the other chargers which we didn't talk about, and we did look at one of them, the Autel Maxi charger, that had both a low voltage component and a high voltage component. And if you want to set it up in a way to test safely and not electrocute yourself from the high voltage component, then there's a lot of safety precautions which you kind of need to take around these. ZDI released a good blog post about how to set up benchtop testing environments of EV chargers and separate the low voltage and high voltage components out to actually do the testing. And I think like a future kind of call to research and like future research ideas for people if you are interested in this sphere, then like, can you actually physically damage charges? Like, can you remove the safety components, like the safety systems and things like that? Is it actually like, because people have been going like, okay, well, maybe we could do this, maybe we could do that, but actually in like proof of concepts, there hasn't really been that much out there. So it'd be like interesting to see. And can you damage cars as well? Like, can you actually physically damage cars? Or yeah, that's an interesting research question as well. So I just want to say thank you to a few people as well. So thanks to ZDI, Trend Micro for running a really good competition. It takes a really lot of organization to run Pwn2Own, to actually like get everything set up, and you don't really see that from like from the competitor side that much. We just kind of like go there and hope everything works, and yeah, there's a lot of admin there. Phoenix Contact, their P-Cert. It's good when a vendor is actually like responding to issues, patching things quickly, good communication. We reported some bugs to Phoenix Contact outside of Pwn2Own directly to them, and they got patches out before our talk. We told them we were presenting at 44Con and Rome Hack, and they were like, yeah, we'll get patches out. So that was cool. Some of the other vendors who participated in Pwn2Own were less responsive and still haven't published patches. So yeah. Then and NCC's transport practice as well, which is like, we're not actually automotive security experts. This is my first time looking at like automotive components, but there's like a good amount of automotive knowledge to draw and hardware security experience as well in the background from my team, from the company. So yeah, are there any questions? Thank you.
Do either of you have an electric car? And if you do, which charger do you have?
You would answer.
Yeah, I do, but I don't even use a charger. I just use 3-pin plugs at home. Not for any specific reason other than, yeah. But no.
Hey guys, great talk. Thank you so much. Could you go back to the demo for the?
There you go.
Which, the second?
Yeah, this one. Could you play it again? Sorry.
Yeah. That's the part where it does the uploading.
Is this where we've missed a vulnerability? There's another one here. Like, yeah.
This isn't in real time as well. So like from end to end, this was a bit sped up in the video, but end to end it was about 8 minutes or so because of the various reboots it had to do, changing from like client mode to server mode and from server mode to client mode. Yeah. So it resets the passwords, but before SSH, the SSH service took a while to actually get access, just for the entire system to boot up and get access to the SSH. That was like 11 minutes or so, and just based on the 10-minute rule, yeah, we just went for the light show just to play the game.